All right, if we insist that we would like a mathematical solution for this, CAMG is going to help you do that. You can ask by going to the file and then producing the records and the files that come out naturally from a bond graph model, and the KMG will produce the equations like this, as you see it in here. The difference between these equations and the ones that normally don't have derivative causality is that you have this derivative on the right hand side, as you see. And also the new thing is that you have an auxiliary equation in there. Okay, so given this situation, we can do the substitutions and produce the fact that it has three integral forms. You have this 2c and the I elements in there, and you have one more equation that actually has the derivative dp sub 6. But you see, the situation here is that these equations that you see, they present a major challenge because they have derivatives on the right hand side. So I'm going to propose a solution in here that would examine the fact that you have this Cauchy form of the equations with derivatives on the right hand side. Remember, the Cauchy form of the equations were used to find the state space form. So what I'm thinking is that we could find a way to manipulate the original system of the state space form derived from these Cauchy equations and see if we can find a solution to the derivative causality problem. The way we do this is to recognize that this system of equations that you have in here, this one here, I know, I only wanted to highlight those three, but it's not allowing me to. Let me maybe I'll just use the pointer here. This three in here plus this form a new set of, x dot is equal to ax plus bu, but it has this E matrix that multiplies the derivatives, you see? And then, of course, it has a new one that has x dot is equal to some matrix F plus the state variable here. So the problem here is that you have in here that you can write this system of equations in terms of the original AB plus this E matrix and this F matrix, which would be derived from here. Okay? So if that's the case, here's where we propose the solution. Okay, if you have the system in here, just like I did it on the previous slide, so that you see that we're talking about the same thing. Okay, in here you have that x dot is equal to ax plus bu plus ef. If you substitute this over from here, right there, and then you recognize you have two derivative terms on both sides, so we're gonna bring this one to the other side like that, factor it up, and then get rid of this matrix in here. How are we going to do that? Is by multiplying both sides by the inverse. So if you multiply that, you have this on the right hand side. At this point you have produced this would become a new A matrix. This would become a new B matrix, like this. So there it is. So you have x dot ax plus bu, and in here you will have this, of course you have the outputs in here, and then you will have this new A and the new B matrix. See, if you do this, in other words, let me go back for a second. When you have the new A and new B matrix, you have solved the derivative problem, but you have solved it mathematically, not by modifying the system, which maybe is the best approach to do, is to examine if you can modify the system a little bit to include other effects, or maybe you did one too many. So in here, if you have this, we can find out the equivalent A new by doing this matrix operation. And so this is the new matrix. So this is by doing this. So to answer the question as to how you would do it in MATLAB, the answer is by finding the E and the F matrix, you calculate new A and let MATLAB do it. So here's a system without derivative form, and this is the system by using this. You're moving it to the other side. You will have this by using the method that I described. This would be the matrix in here. This could be extended in case, looking here, I put just a connecting rod and really messed up the system. We have 3 now in derivative form. And if we continue messing up the system, put 2 springs together and you add 1 C. 4 derivative forms, it would be, you would think that it would be almost impossible to do this. No, by this method that I showed you, there's the 4 derivative forms, produce this set of equations for derivative forms, and produce these 4 dependent derivative equations also in the form that I have shown you. So if you find the E and the F matrix, if you do that, then run it, you will get this equivalence. In other words, we'll get rid of the derivative causality by finding equivalent elements, and in this case it would be this one. So, but just to give you an idea, this is without the derivative causality. The E matrix, of course, becomes more complex. But there is a solution. Even if you have it like this, you will have the new A matrix like this by using the method that we have outlined in here. And the B matrix also would be calculated in the same way. Okay, so that is the solution to the mathematical solution to the derivative causality problem.